and thank you for joining us today. Our webinar titled Be First to Market with DDR5, Here's How. My name is Bob Potok with Zuken, and I will be the webinar moderator today. We have a great team of subject matter experts from Keysight Technologies and Zuken to talk about DDR5 implementation. But before we meet our presenters, there are a couple housekeeping items that I need to cover. First, you are encouraged to ask questions throughout the webinar. Please submit your questions in the questions window and we will answer them during the presentation or during the Q&A session at the end of the webinar. We will also be asking 3 polling questions during the webinar, and we will be sharing the results so you can see how others are responding as well. It's always interesting to hear your responses to these polling questions, so we really encourage you to participate in the poll. And as I said earlier, you will be able to see the results. So your participation is greatly appreciated. And as I mentioned earlier, we have a great team of subject matter experts. We're joined today by Stephen Slater and Tim Wang Lee from Keysight Technologies. Stephen is currently the SI and PI Simulation Solutions Manager at Keysight. He has a decade of experience in the EDA industry as an applications engineer and business development manager for high-speed digital and wireless comms. Tim is a signal integrity application scientist at Keysight. He is currently a PhD candidate concentrating on signal integrity research for simulation and measurement correlation. Welcome to both of you. We're also joined by Tanir Day from Zuken. Tanir is an applications engineer at Zuken, working closely with customers on board-based systems design, focusing on chip package board co-design. Welcome to you, Tanir. So welcome to you all. Thank you for being here today. And with that, I'm going to turn it over to Stephen and let's get started.
Thank you very much, Bob. So first thing we want to do when we talk about DDR5 is first take a look back at how we got there. So let's take a trip down memory lane and look at DDR2 and DDR3. When we were designing for DDR2 and DDR3, everything was all about caring about our data lines as being transmission lines with reflections, but we cared mostly about measuring setup and hold times and skew between our traces. Those setup and hold times, if we want to make sure that we were in compliance, we needed to first compute the slew rate of our signal and then look up the speed grade and find out what the compliance limit would be. But as we moved forward into DDR4, there was much less margin to work with, and they started to decide, or JEDEC determined that actually we'd be leaving margin on the table if we computed setup and hold times for the data specifically. So they introduced something this called a receive bit error rate mask, and this then specifies an area or a region where if you keep your signal outside of that box, outside of the mask, then you can achieve a system bit error rate 1e to the minus 16. The other things that they did with DDR4 was try to reduce power consumption. They did that by ways of, or methods of moving to a pseudo open drain as the IO technology. And that means that you only then draw current when you're driving for a 0. And then they also managed to use data bus inversion, which would make sure that if we're only going to draw current during zeros, that we minimize the number of zeros across a byte lane. And also, of course, reducing the supply voltage as well down to 1.2. Now, as we move to DDR5, we reduce that voltage even further, so it's 1.1. But the input now to the DRAM has an I which is nearly collapsed. So therefore, there's a lot more intersymbol interference in the channel, and we talk about the channel as having an impulse response that needs to be equalized. Many more of the specs are related to statistical values like random jitter, deterministic jitter, random noise, and deterministic noise. And you can see that the top speed grade that they're shooting for is 6400, but there's already discussions about how to take it even faster than that. So in order to be successful in DDR5, there's actually a lot that goes into it. So your very first product that you design, if something doesn't work, then how are we going to debug and determine where we are? So first thing we want to do is think about logic analysis and protocol. This would be able to tell us whether we've got issues on the read or write, whether the issues that we have are during preamble or postamble. We could determine if our burst length is inaccurate. And then once we know which particular lines are challenging or which particular lines have an issue, we could then go in and probe. Probing means that we need brand new risers and interposers designed for DDR5, redesigned so that they have very minimal crosstalk and they're not increasing the loading on the channel. Then we also need brand new test fixtures which enable test and measurement equipment to be able to access and break out the signals that we want to be able to receive. For transmission test, TX test, we use a real-time oscilloscope running Keysight's compliance applications. But in DDR5 now we spend more time as well using jitter separation techniques in order to look at transmit jitter in terms of random and deterministic separation noise. Then for receive test, this is something that's brand new to DDR for the first time. So we've got an arbitrary waveform generator and a data acquisition unit, really wide bandwidth, that's able to perform a full loopback bit error rate test. But sometimes signal integrity of on your PCB is not only about the channel, it also matters for the power planes as well. So the noise on the power planes and how they affect signal integrity, we need to be able to measure that power noise first. So we can do that with these very low noise probes, as well as they're designed to be able to connect into power planes that have a very low impedance. But mostly what we're going to be talking about today in this webinar is physical layout, which we're performing with CR8000, and modeling and simulation, which we're performing in Pathwave ADS. So our agenda for today is firstly we're going to spend a little bit of time talking about the challenges of DDR5. Then we'll move into pre-layout exploration with ADS. We'll look at routing of DDR signals in CR8000 and some of the cool new features there that enable a fast physical layout. And then moving into post-layout EM extraction. And finally, we'll round off with some final system simulation metrics and new test techniques. Okay, so DDR5 is mostly about how we're going to handle RX equalization on the DRAM. This is the newest thing that's been introduced that is going to create a big change to the modeling ecosystem as well as the measurement ecosystem as well. So what happens here, as you can see in the top left-hand corner, we want to put through a beautiful square wave for our digital signals, but actually what makes it through to the other side is this single pulse response that much of our energy is smeared into future bits. You can see from this diagram that we've got two slices which are making the decision thresholds. They are then feeding back into the DFE taps. And in the bottom right-hand side, you can now see what the variable gain has done to equalize the main pulse and what the DFE has done, that's decision feedback equalization, to remove the signal energy that was in those next unit intervals. Now, something that's interesting about this is that in high-speed serial, usually you would have an embedded clock. So the clock is inside the data, and we have to use clock and data recovery to pull out the timing. But in DDR, the timing is provided externally via DQS, which is the strobe or the clock for the data. But up inside the DRAM, we've got a clock tree, and that can introduce some skew between the data strobe and the data. and this is going to have an impact on how well the equalization performs. The other takeaway I'd like you to have from this slide is that we have a DRAM mode register, which you can set the mode register to control the variable gain, the VREF DQ offset, and the individual DFE taps. But we do this for every single DQ. So when it comes to simulation and for measurement, there's a huge number of controls that we have over setting up this equalization. The next thing is that in DDR5, the RX specifications are moving to be inside the die. So traditionally, DDR3, you take a look, specifications like setup and hold, they're always at the balls of the DRAM. But now we expect, especially for DQ, a nearly closed die. So they move many of the specifications inside after equalization. That has some big implications for both simulation and for measurement. And we're going to be spending a little bit more time talking about that later in the webinar. The next thing is that the specs themselves are becoming much more bit error rate focused. So from the draft spec of DDR5, you definitely find specifications for maximum jitter, for deterministic and random jitter, and duty cycle distortion. But the next thing is that they do also mention that if you want 99.5% confidence that you're going to get to a 1e to the minus 16 system bit error rate, then you need to actually capture in measurement 5.3 billion UIs. In order to do this loopback testing, one thing that they do is they create a stressed die to input into the device under test. The stressed die we'll talk about in a little bit more detail later on. And finally, we want to discuss jitter and the impacts of jitter. So when we talk about a system bit error rate of 1e to the minus 16, in simulation, we need to be able to determine how closed our eye is going to be down to that level. So here what you really want to look at is the red bit error rate contour. That's showing you just how closed the eye is at 1e to the minus 16. You can see on the left-hand side, this is at the speed grades of DDR4 1600, and then on the right-hand side at the faster speed of DDR5 4800. And the eye closure, or the timing margin reduction due to jitter, in this case happens to be 47%. So it's very significant. It's something that we can't disregard. We need to be able to know and predict what our margin to mask actually is. And so now at this point, before we move over into pre-layout exploration, we'd like to take a moment to ask you to answer a poll question.
Thank you, Stephen. It is time for our first polling question. And that first polling question is, what is your current role? Hardware engineer, PCB layout engineer, signal integrity specialist, engineering manager, or other? And if it is other, if you could just tell us what that is in the questions panel, that would be very helpful. I see the answers are coming in right now. Thank you again to everyone for participating in our poll. As I said earlier, it's always very interesting to see how people respond to our polling questions, and I'll be sharing the responses here in a moment. We are getting some great participation right now. We're at over 80%, and I'm just going to give everybody another 5 seconds or so, and then we will close it and share those results. All right, why don't we go ahead and close that poll. Okay, so here's what we have in terms of polling results. What is your current role? In terms of the audience, 27% of you identify yourselves as a hardware engineer, 10% as PCB layout engineers, 42% signal integrity specialists, 13% engineering managers, and 8% others. And if I look at some of the others, it looks like it has to do with some manufacturing roles as well. So thanks again, everyone, for participating. I'm going to close this poll and turn it back over to our presenters.
Thank you, Bob, and thank you for the answers. Now, before I start the pre-layout section, I would like to show you something that scares us the most. That is the closed eye. When we see the closed eye, we start thinking about these questions. First, what are the possible causes of a closed eye? And we come up with a list of possible solutions to the problem. Then at the end, we ask another question. We ask, how do I troubleshoot? Now, let me introduce you to a new predictive, productive, and insightful workflow that will help you troubleshoot. And that is for DDR5 specifically, is the DDR5 virtual design prototype. It is productive because it simplifies the troubleshooting process. And it is insightful because you get to understand your design limitations by looking at the virtual prototype. Finally, it is predictive because you get to explore design space for the future in a virtual workspace. Now here we have a designer, Bill. He's using a traditional design process where based on vendor guidance, fabrication prototype, and measure and verification, you'll be able to create this channel and measure. Now, when Bob measures an open eye, everything is great. And he would say, my work is done here. However, when Bill measures a closed eye, again, we'll have to come up with a list of questions and then troubleshoot. With Bill's approach, when Bill sees a closed eye and come up with the possible root causes for DDR3 or DDR4, now with DDR5, with on-die terminations, DFE equalization tabs, and different silicon process corners, it will be hard for Bill to troubleshoot and to explore because those are not part of the design process. Now, designer Dave has a different approach where he uses virtual design prototype, where he first create the prototype and then validate and simulate, fabricate, same channel as Bill, and finally measure and verify performance. The beauty in Dave's approach is such that when a closed eye presents itself and possible root causes are there, we can go back to our virtual prototype and see whether or not our root causes are the one that we think of. Are they solving our problem? Now, with the incoming DDR5 RX DFE tabs, on-die termination settings, and silicon process corners, those can be easily incorporated into the virtual prototype and test. Now, how does that look like in a DDR5 channel? That is a DDR5 golden channel proposing by Keysight. On the TX side, as Stephen mentioned, from speed grade to 3200 to 6400, now we're looking at 8400 with different data patterns, jitter, random jitter, deterministic jitter, and TX de-emphasis, pre-emphasis on the TX side. Now in the package, we know they're important because it shows how things are connected. And since DDR is a reflection and crosstalk dominant channel, we need to have these parasitics, sockets, and PCBVS correctly modeled in different formats. Now, as the signal makes its way to the open field, because again, DDR is a reflection and crosstalk dominant channel, we have to take a look at the impedance and the crosstalk level between the traces. And as Stephen will mention later on, the DQS is very important as well. Next, finally, the receiver parameters. Now we know we have on-die termination settings and RX equalization in DDR5. Now the reflection from the connectors will play an important role on how the RX equalization should adjust itself. So those are all very important parameters. Now altogether, this is the next-gen design philosophy. It is better to fail after a mass simulation than after a mass production. And DDR5 Golden Channel will help you avoid those fail after mass production. And here's a list of parameters that the JEDEC standard is going to look into sweep for the Golden Channel. From here, We can see the data rate is being swept, the ranks, data patterns, transaction times, and various interconnect and receiver properties. And I want to make a note here that Keysight is working really closely with industry leaders on all aspects of DDR5. As Stephen mentioned, we are encompassing a lot of ground here. Finally, I would like to show you a demo of the virtual design prototype in Keysight 80. Here is a golden channel. And without EQ on the receiver side, the eye is closed. And after we turn on the correct DFE settings, the eye will be open. First, what we can look at is the TX settings, where we can configure the emphasis, pre-emphasis, and the data rate. When we come to the models and touchstones files for the package, socket, and VIA. Now we know for DDR5, the crosstalk dominant channel and impedance dominant channel reflection, we have to look at the substrate and how controlled impedance play a very important role. This control impedance line designer in ADS can help you design and define the trace specifically as you would in a channel design, and the length as well. And after the simulation is done, you'll be able to quickly view how this cross-section provide the impedance and the loss. And VIA also plays an important role. And here's where we'll use a VIA designer that gives us an interactive VIA modeling environment. And after we model it, we'll be able to see an S parameter generated by the 3D full wave simulation. After defining our trace and VIA, the next most important thing is the RX settings, undetermination, DFE, and such. With the correct settings and you simulate, you'll be able to observe that on the left, without equalization, the eye is closed, and with the proper equalization, the eye is open. That is a DDR5 golden channel. Now here's a recap of the virtual design prototype, the productive, insightful, and predictive approach. It is productive because it connects the real world to the virtual world. It simplifies the troubleshooting process. Next, it is insightful because you get to understand the design limitations by doing sweeps as one would do in the DDR5 golden channel. Finally, it is predictive because explore the design space for the future. You get to turn on your receiver and then transmitter, the speed to 8400, and you will see what's going to happen for that speed grade. Now next up is Tunier with Zuken's DDR4 8000. But before that, we have another polling question. Bob, take it away.
Thanks, Tim. This will be our second of 3 polling questions, and let me launch that polling question. This one is, what is your top concern regarding starting a DDR5 design? Crosstalk, simulation complexity, equalization, model availability, or other? And again, please provide that response in the question panel. And again, we appreciate your participation in our polling questions. It's always interesting to hear your thoughts. And again, we're getting great response from the audience. Thank you very much. I'm going to let this run a little bit longer. And we are approaching 80%. So I'm going to give everyone another 5 seconds. If you would just mind providing us with an answer, that would be great. They're still coming in, so I'm just going to wait another second or 2. All right, very good. Thanks everyone for participating. I'm going to close this poll and share it with you. So what is your top concern regarding a DDR5 design? 15%, our top response was simulation complexity, so that must be weighing heavy on everyone's mind. Our second highest concern is model availability, followed by crosstalk, equalization, and other. And I don't have any answers for other right now. So it looks like simulation complexity is definitely the largest concern in a DDR5 design. And with that, I am going to pass it back to Tanir. Thanks, everyone.
So first of all, I'm going to introduce you ZUKEN CR8000 to design your DDR5, and then I'm going to talk about some design challenges you may face. ZUKEN CR8000 brings extensive schematic design, simulation, and analysis capabilities, which helps to manage and make the optimal use of your engineering design data across the engineering teams. Intelligent multi-board and embedded high-speed design is inherently supported in ZUKEN CR8000. Next. ZUKEN CR8000 enables design teams to lay out their DDR5 design in the context of a complete system or product. As we know, the DDR5 RDIMM features also contains 288 pins on a slightly curved edge connector, so its layout and design are a bit different when compared to DDR4 to avoid the insertion of DDR5 modules into DDR4 slots and vice versa. So ZUKEN CR8000 that inherently supporting any high-speed layout designs like DDR5 and PCB engineers can conduct SI, EMC, and PI analysis concurrently, managing constraints and auto-routing your board all in one environment. Next. So as you know, large-scale integration is a silicon technology, and this manufacturing process is different from package and PCB. So CAD database should be different in each object. CR8000 can handle these different objects in one system by embedding open access database. Next. Now I'd like to talk about some design challenges. One of the things is topology template, and using the topology template in your DDR5 design, you can rule out the wiring method of high-speed signals that is recommended by DDR design guideline. You can use DDR5 design support functions according to the design guideline for the connection order, placement, and routing functions of unconnected nets of the canvas. So why this topology template is so important when you are considering your DDR5 layout designs? The first thing is your noise level on a trace is highly dependent on the topology you have been selected. The topology template refers to the alignment order of the wiring and also the wiring structure of a network. For an example, you have a multi-network load, and according to the actual situation, selecting the appropriate cabling topologies and take the right to the termination is very important. And also, like when we do the high-speed layout designs, we have to take care of our track lengths, widths, spacing, and that has to be greatly reducing the efforts, and also configuring the managing constraints has to be considered. Next. Bus route is a function that generates a pattern in your DDR5 layout canvas. It comes up with an obstacle that avoided near the specified route by roughly instructing the route of the net, and that is to be routed with a bundle such as bus or differential pair. And this bus route is only available when you have your intelligent placement or router is enabled in ZUKEN CR8000. Another key thing is auto routing. If you have an input in your unconnected net or two objects, that to be routed directly automatically perform the routing between 2 points. So this bus routing and auto routing, why these two steps is essential for DDR5 layout. So it is like a channel, routing channel, where the layout designers can visualize the paths between the critical components. Often bus planning is tied in with the component placement, and also several iterations of component placement planning are required before starting layout is found. So you just can think of a bus planning is like a sketch, and it's like a sketch stage where the general outlines of pictures are drawn. One of the major, next please. One of the major issue in high-speed design world is called crosstalk. And when you talk about the crosstalk, and if it's DDR5, it's more serious. So crosstalk is an unintentional electromagnetic coupling between the traces on a printed circuit board. So for an instance, if you have multiple signal vias in your DDR5 layout and you have DQ0, DQ1, DQ2, maybe DQ3 and 4, all are sharing one ground via, and they are coming back in the same localized area, and that's gonna cause your crosstalk. This is not just trace to trace crosstalk, which happens when you have two traces very close together. This is a crosstalk because you have many signal vias and that sharing one common ground via. So why crosstalk is so important in this DDR5 designing? Well, technically, traces that are routed in parallel will form a coupling capacitance and coupling inductance, and both this too is depending on your distance of the traces and the dielectric environment, length or distance at which the traces are routed, and also the traces are closer together, the longer in parallel they are more coupling. So the amplitude of the crosstalk, they're depending on the rise and fall time of the aggressor signals, which means the same PCB layout might perform better or worse sometimes. Next. The online DRC rule checking runs in the background in real-time flagging or automatically preventing the design rule violation from your DDR5 board. This is especially helpful when interactively routing your DDR board to immediately highlight clearance, width, and the parallel segments violations, and also it checks the component positions as well. So one of the key part for DDR5 is the 3D vias. So why we have to think about the vias when we are doing the DDR5 design? So the perceived negative effects of vias may fall into one and several categories. One of the things is vias are inherently capacitive and change the characteristic impedance of the trace. Via can cause a step function, change the trace impedance, and therefore cause the reflections as well. And when a trace moves from like one layer to another layer, it becomes referenced to a different reference plane, therefore severely distorting the characteristic impedance of the trace happens. So just make it as a simple thing. Like for instance, if you have a signal, it's not just something that the electrons are going on, it's actually an electromagnetic wave which has a signal and a reference. So we need to think about where the reference is. If you have an ideal ground plane and you have a signal traveling over it, okay, you're good to go. But how about you have a multi-layer PCB and it could be maybe 8 layer, 10 layer, 14 layer, and there's a signal via is going from top layer to bottom layer. And where is the return path for the signal via? If you do not have a close by stitching via so that it offers a return path for the signal via, you are going to get all those kind of signal noises. So via might come more critical in DDR5 high-speed data transfer. So this is one of the key part when we're going to design this DDR5 layout. Next. For a complete RF and DDR5 high-speed verification flow, CR8000 designed for interfaces with the best class high-speed RF and EM analysis solutions. DesignForce offers the high-speed designers to use an interface to extract the complete or partial designs along with the material and substrate information and export them for analysis in Keysight tool. For board layout analysis, an ABL file format exported using the layout data created with the DesignForce with 3 output options. One is the ADS circuit simulator, ADS momentum for EM analysis, and also ADS SI and PI Pro. So what are the information you need in Keysight tool from Zuken CR8000 tool to effectively run a DDR5 simulation? The basic thing, you need a board layout file from Zuken CR8000. You need to make sure that your board file is accurate, your stack-up is accurate, your material and substrate information is accurate. You have to make sure your IBIS models are also perfect if you have an IC on your board. Zuken provide the right stack-up and material information to Keysight through ABL, and then Keysight can take care of your simulation part. Now I'm going to hand over to Stephen, and he is going to talk about the post-layout EM extraction. Before that, there are polling questions for you.
Thanks, Tanir. And yes, this is our third and final polling question. The question is, when will you start a DDR5 project? Do you have one in process today, within the next 3 months, by the end of next year, or you have no plan? And again, we really appreciate your participation. We'll be sharing those results with our audience. And the voting is coming in. Thanks again. We're climbing up over 60–70% right now. And I am going to let this run a few more seconds since people are still voting and we still have numbers coming in. Great. All right. 5 more seconds if anyone has a last-minute vote that they would like to contribute to the poll. All right, great. I think we'll close that right now with great participation. Thank you, everyone. Let me share those results. So the question is, when will you start a DDR5 project? And the most common response, no plan at this time. Fair enough. The second most popular answer is that they have one in process. 13% by the end of next year and 8% within the next 3 months. So great responses. Thanks, everyone. Very interesting responses as well as in terms of DDR5. All right, I'm going to close out this poll and I'm going to hand it back over to Stephen. Thanks.
Thank you very much, Bob and Tanir. So we're going to move now into the post-layout EM section of our discussion, and Tanir talked a lot about crosstalk and crosstalk estimation. And what we want to do is we want to analyze why crosstalk is such a big deal for DDR5 4800. So what we have so far on this left-hand side is eye closure that's just due to ISI from the channel. There's no crosstalk and no jitter at this point. The next thing is you see these set of traces here where the pins start together and then they also end together. These are neighbors, and together at the Nyquist frequency for 4800, we've got less than -25 dB of couplings. This is the near-end crosstalk and far-end crosstalk for one of the victim lines and its nearest neighbors. So we might take a look at that and say that that is, fairly reasonable. But the question you might have is, well, what's causing the crosstalk to be higher or lower? Well, actually, one of the things you need to be careful of is that in DDR, you have many more signal pins in the pin field than you actually have ground or power pins. So when we talk about return current path, one of the things that's going to increase our crosstalk is when we're sharing ground pins for the return current path. So you see in this case, we've got 2 signal pins, and the closest ground stitching via, there's just one of them. We can't do much about that because you're limited on the BGA as to how you utilize those pins. But one thing we can do is make sure that if our pins start together, make sure that they don't end together. So making sure that we route our signals such that, or choose IOs that end up being separated. Finally, we can see that even with minus 25 dB of near-end crosstalk, far-end crosstalk, it still adds a significant amount of I reduction. In this case, it was about 37% of voltage margin reduction, and also it does impact the timing margin to a smaller amount as well. Now, when we talk about post-layout EM extraction, what I'll be demonstrating today is SI Pro, which is available inside of ADS. The reason why we use SI Pro is because it's an EM tool designed for high-speed digital PCBs. That means that it can handle PCBs that have a very high layer count. And the other thing we care about is making sure that we can handle a large number of nets at once. But crucially, any EM tool needs to be very accurate. So in this case, our solution does not use any transmission line models. What it does is we use a 3D planar technique called method of moments for the traces. And when it comes to the vias and transitions from via to strip line, that is handled with a finite element method solver. So together you have two pure EM techniques that are combined into one simulation engine. And we get our results that are accurate, but in a very practical simulation time. So now we're going to take a look at the SI Pro and Memory Designer workflow. So here's the layout that's been imported from Zuken into this into ADS. You can see this board is provided by Seiko, which is a company working on embedded computer systems for medical automation. And once we've imported the board, the next thing you want to do before you run any EM simulation is check the substrate stack up and make sure that material properties are set correctly. So making sure that we might want to apply surface roughness, for instance, to some of the traces, making sure that we've got the right dielectric permittivity set. And then now I'm opening it up in SI Pro, which is a 3D environment. So you can see that we can take a look at our board that's coming in. I'm then launching a new DDR setup wizard, and we created this to help cut through the simulation setup complexity. So effectively, all I need to do is select, which is the memory controller and, which of the components happen to be memory devices. Those two things we're clicking on are actually connectors. They're connectors for an SODIMM. And then we calculate, based on net names, what are all of the data, the data strobe, the command address, clock nets. We provide all of those, and as a user, you select which ones you want to add to the simulation. Now, something that's very special here is we allow the user to specify for the command address lines the ability to be referenced to a power net. And we'll see in a moment, once we generate the setup, why that's very important. So generating the setup goes and creates the new analysis. And then now we're going to go and have a look at what we're actually simulating in that analysis. So we're verifying that those additional nets were added. So you see all the data nets, but we've got a couple of command address nets. So now I'm going to peel away the different layers. So first we turn to a wireframe mode, turn off the connectors, then just hide everything and just look at the selected nets. You can see that we've got some blind vias, but then through sequential lamination with micro vias on top, we see how it's created. Now this points out why we need a power net reference. It's because the signal return current path is actually flowing through the power plane. This is quite usual for these types of simulations where we're using a DIMM. So simulation stats, there was 15 ports, 30 frequency points, and 22 minutes. And now what we're going to do is export the model. So we export this EM model to automatically create this schematic. And now how are we going to consume that EM model? Well, we're going to use a different feature in ADS called Memory Designer. And for this printed circuit board here, we get to reference that, that cell that we'd created that was exported from SI Pro. Then next, we're going to use bus wires to connect. These bus wires are very intelligent because now they can do an automatic connection based upon signal IDs. So if I press auto connect, you'll see that it connects everything that has the same signal ID, but crucially, it tells us if there's anything that may not be quite right. So in that case, it was showing us that the pin on the layout doesn't exactly match the pin on the IBIS model. Plugging in to have a look at how we set up the IBIS model, you see we choose which is the device that we want to instantiate, then next from the IBIS model, which are the nets we want to simulate, and then now for groups of nets, we get to choose the model selector. The final thing I want to look at is the memory probe. Now the memory probe itself is very special because it doesn't have to be wired into anything at all. It can access all of those signals within each of those special smart components. So we add our signals as groups, and next we select for groups what types of measurements do we want to make. And finally, we can invoke a compliance test which calls Keysight's TX compliance application. This Memory Designer handles two different types of simulation modes, either transient SPICE or DDR SPUSSIM. And you see the results here. We've got both the compliance report if we drive the Keysight compliance test, as well as you saw some eye diagrams for DQS and DQ command address, etc., and being able to plot the receive bit error rate margin. Okay, so now we're going to move into the final part of our discussion today. We're going to look at final system simulation and test techniques. So we talked about using Memory Designer for system simulation. Something which I haven't mentioned up until this point, though, is how are we going to handle the equalization models. So this is very interesting, and in fact, we've got a whole other webinar that will be coming up soon to discuss how IBIS AMI is being used in bit-by-bit bus simulation for DDR5. But at least I can tell you today that in ADS 2020 Update 1, which is shipping later in November, we will be able to use the IBIS AMI models for DDR5. And many of the silicon vendors out there are already investing in developing such models. So this is a new technique, a new technology, and yeah, please stay tuned for more information later on. So let's take a look at some test techniques. So one of the things that's challenging for TX test is that when we talk about DDR5, we expect the eye to be nearly closed at the input to the DRAM. That's a challenge because how are we going to be able to perform some of the measurements like the receive bit error rate mask measurement when we don't have an open eye to compute the mask on? So what's being proposed at this point, it's not quite in the draft spec, but being proposed, is the capability to make the measurement at the DRAM ball, to use the S parameters for the package of the DRAM and to put that into a package model inside the oscilloscope's InfiniSim software. It will de-embed the package model now, so now we get to see what the eye looks like after the package. And then inside the scope, we can use InfiniSim again to be able to apply receiver equalization. So we can put in CTLE to represent the variable gain, and then multiple taps, adaptive DFE taps, even though in real life in the DRAM, they won't be adaptive, but as a user, you'll want to be able to have those taps, adapt themselves directly. And then that gives us what the waveform is going to look like, virtually probed. And now we can construct our eye diagram, put a receive bit error rate mask in the center, and then compute eye contours to see just how close the eye is going to be at 1e to the minus 16. So this is a big change for transmit test, but there's also big changes for receive test as well. Okay, so this is the case of receive test. And the idea is that we would use a stress die generator. So in this case, we're using it's a loopback bit error rate tester, where on the arbitrary waveform generator, we have the ability to input a cocktail of random jitter, sinusoidal jitter, and aggressive signals as crosstalk, such that we can create a stressed eye. The stressed eye is defined in the specification, and it's in the draft spec now, and that would then be input into the device under test. So through the system, the DIMM, the package, and into the die. And this is something that's very special for DDR5, brand new, it's never been seen before, is the case of having loopback pins. So before, once the signal is equalized, before it's written to the memory core, the signal can come straight back out through dedicated I/O pins on the DRAM, and that then can be sent back to the bit error rate tester. And we can do this, brute force bit error rate test, where if we can capture 5.3 billion bits, then we have 99.5% confidence that we've met the system bit error rate. And so finally, in summary, I'd like to have the takeaway that DDR5 offers some great additional bandwidth. It's much faster, but there's also a lot of challenges out there. In which case, who would be the best partner to work with to help guide you through to first product success? We'd like to think that Keysight, together with Zuken, could be that partner working with you. And if you have any further questions, we'd be very happy to answer them for you. So at that point, I'd like to thank you very much and pass back to Bob.
Thank you, Stephen. We do have a couple questions from our audience that this would be a good time to address. Alex is asking about the availability of DDR5 IBIS models. I was wondering if someone could comment on that.
Yeah, sure. I'll take that at the moment. So, as we work with many silicon vendors, we're definitely aware of their efforts to start working on IBIS AMI models. Some of those say very far along now. At this point in time, because the silicon vendors don't have they have sample chips at the moment. I think it's a little early for them to be sharing models to their customers. What can be done is, firstly, you have to push upon your silicon vendor to get the model as soon as possible. But in the meantime, Keysight has the ability to provide you with generic AMI models. So what I mean by that is you can use a standard IBIS model, adjust it so that you can add the AMI model to it, which Keysight can provide, and then you'd have the ability to be able to perform variable gain, skew adjustment, and RX DFE tap settings. So yeah, there's definitely things that you can do today to get started with your DDR5 exploration work.
Okay, great. Thanks, Stephen. I got another question from Abinash. What is a typical simulation runtime for a 2-channel DDR, 32-bit?
Okay, depends whether we're talking about EM simulation. EM simulation is takes much more time than the system simulation part. But actually, that's a really good point, because this is one of the things that IBIS AMI and an enhanced channel simulation for DDR gives you over something like standard transient spice. Standard transient spice tends to take quite a long time. We tend to want to simulate hundreds of bits or maybe low number of thousands of bits with transient spice. But when we talk about IBIS AMI with an enhanced channel sim for DDR, you're talking about being able to simulate millions of bits in tens of minutes. So we'd be feeling quite comfortable about being able to simulate, let's say, 10 million bits through the channel, within let's say 30 minutes, and then from that you have a reasonably rich data set to be able to extrapolate the eye contours to a reasonable amount of accuracy, and yeah, so that probably gives you a reasonable picture of the two types of simulation techniques. When it comes to EM simulation, well, that's probably what we kind of showed before. 15 ports, so the equivalent of about 8 to 10 nets, and that simulation took about sort of 20 minutes to simulate.
Great, thanks. Another question from Tom. What is the main PCB routing challenge for DDR5 designs?
Well, I'll take a crack at it, and then maybe also we can pass to Nia for his inputs as well. For me, one of the things that's been a perpetual issue for DDR4 and then into now DDR5 is it's just the constraints. So, for instance, you're trying to make sure that you can keep your data bus, so inside a byte lane, trying to make sure that you're keeping skew under control. And here's one of the challenges: if you too tightly constrain the skew, it means you're ending up adding in lots of switchbacks or serpentine, which makes the actual fitting all of your data nets into a certain real estate on the PCB pretty hard. So usually we say that the memory controller has the ability to dial out a certain amount of skew. It does a calibration. That can be handled in simulation, by the way, with right leveling. So that is handled in simulation too. But we try to say that keeping within 10 picoseconds, 5 picoseconds of skew is between lines. That tends to be something which is a challenge, but something which becomes necessary. One more thing which I could probably mention is knowing a little bit about the DRAM is when you come to route DRAM in a solder down design, each DRAMs for command address buses, they provide a capacitive loading. So what you need to do is that even though you might be designing for say like 40 ohm transmission lines, once you start getting close to the DRAM and going between the DRAM, they actually decrease the width of the traces so that they become 60 ohm impedance, such that now it kind of balances, that higher impedance balances with the capacitive loading that the DRAMs are providing. So these are some of the challenges, and this is one of the reasons why EM verification is pretty important at the end to make sure that we're going to get the performance we want out of the layout.
Great, thanks very much. At this point, I think that's going to conclude our webinar. We're just about out of time, and I'd really like to thank Stephen and Tim and Tanir for providing some great information regarding DDR5 implementation. And for our audience, I hope you found the webinar interesting and helpful in your upcoming DDR5 designs. An on-demand version will be available in the next couple of days, and you'll receive notification. But we also wanted to make you aware of Zuken's technical webinar library. You'll see the URL on the screen. We've got a great variety of webinars. And I also want to remind you about Keysight's upcoming webinar on DDR5 focused on IBIST AMI. That looks like a great webinar as well coming up on the calendar. So again, thank you everyone for attending today's webinar, and I hope you have a great day.